Okay, so we have finished covering the topic of the range. And if you remember when we began discussing the cruise, we said that there's fundamentally going to be two main different questions, right? So the first one was from the given amount of fuel that we have on board, what is the distance that I can cover, right? And this question was answered in a fairly long discussion by the definition of the range, right? So this was the question again of from a given amount of fuel, what is the distance that I can cover? Whether it's a distance relative to the ground, whether or a distance relative to the air. And we also had another question, which was from the given amount of fuel, how long can I stay in the air? Right, so how long can I stay in the air from the given amount of fuel that I have on board? And this question can be answered by the definition of the so-called endurance. And endurance, by definition, is going to be the amount of time that you can stay airborne from a given amount of fuel. So it's basically turning around the same exact question. So it's the amount of time that can be spent airborne from given amount of fuel on board. Okay, so first and foremost, when do you think this endurance can really come into question? Because we said that for most cases, so for flight planning purposes, for alternate planning, and for maybe for commercial purposes, the range is going to be more useful for us than the endurance, right? So when can endurance come in handy, for example? Well, a few scenarios, but the most important is two of the most important. One is when you need to be holding for some reason or another. So holding is usually a standard procedure used mostly in instrument flying, but it can be used in visual flying as well, where for numerous reasons the aircraft needs to be holding, so basically flying in a what is known as a racetrack pattern. So usually you have a fix of some sort, and usually this is some sort of radio navigation station, and you would be flying what is known as a racetrack pattern, right? And the aircraft would be flying around in this pattern until it can proceed. And the different reasons for holding would be, for example, waiting for weather to improve. So waiting for the weather to improve at your destination airfield. It can be congested traffic. So very, very common in very congested airports. For example, in Europe, Heathrow would be a good example, where they have holding patterns where they keep the aircrafts or the aircraft which have just arrived until they send on the approach the airplanes or the aircraft which have arrived earlier. So how they would achieve this is that you guys have probably seen these multi-story parking lots where they have this big parking lot, and it has multiple stories, and on all of the stories they have cars stored, and between them you have the spiraling road, or basically it's a spiraling downward road where the cars can actually come down. right? And they spiral downwards until the floor they want to go to. And usually, you know, the lower floors have the better spots, but you know, if the lower floor becomes, you know, congested with cars, you need to go higher and higher to sort of find the parking spot. And when you want to leave the building, you know, you have to go from all the way up here all the way down here. And the same theory works in these holding patterns when they have this given fix, you know, and this works on like multiple levels, because you would have like one level, or you would have like one airplane, and this would be the lowest level, and you would have like one airplane in this holding pattern, and you would have another holding pattern, you know, above it with the minimum vertical separation. So usually there's like at least 1,000 feet between them, and you have another airplane and this other holding pattern, and so on and so forth, right? So these would be stocked on top of each other, and when the aircraft in the lowest holding pattern can go to the approach, you know, so this one would leave the holding pattern to go and do some sort of an approach. The one on the top would actually descend down to this lower level one, and the one on top of that could descend down to the lower level one, and so on and so forth. And you know, if you have an incoming aircraft from, you know, their en route stage, they would be proceeding to this one. So this would be one another reason why you would be waiting. But a third reason, maybe to reach the maximum landing mass, you know, the structural one. So for example, we've talked about a little bit, you know, about these takeoff and landing masses, but just a little bit. And some of you might know that there are these airplanes, the wide body airplanes. So for example, you can imagine the 747, 767, A380, A330, A340, you know, so the wide body airplanes, usually the ones that fly transatlantic flights and the long haul flights. And for these airplanes, the maximum landing mass is usually much smaller than the maximum takeoff mass. So, and the difference between the two is, of course, you know, the amount of fuel that you have on board. So, I don't know, let's say an example, like you have the maximum takeoff mass to be, you know, 200 tons, and the maximum landing mass to be 100 tons, for example. And between the two, you know, you would have to burn quite a substantial amount of fuel. And this is just an example, so not real life numbers, but just imagine that you've taken off with, you know, 12 hours worth of fuel from, you know, let's say, you know, JFK, you know, in New York, and you're fueled up, you know, like 10-hour flight to go to, or 12-hour flight to go to Vienna, for example. And let's say you have an engine problem or an engine fire after the takeoff, and you manage to take care of that. But of course, you decide with one of your engines damaged not to proceed with the transatlantic flight. So you want to go back to JFK. However, you know, you're still well above your maximum landing mass. So in that case, you would just have to enter a holding pattern to burn some of the fuel that you have on board. But of course, for long-haul airplanes, they also have something known as like jettisoning, where they actually can basically throw this fuel on board or vent this fuel overboard, release it into the atmosphere, let's say, to reduce their mass in a quite short amount of time. So this would be a situation where you would need to be holding, so, or, you know, maximum landing mass, or any sort of like emergency. This could be possible, or, you know, distress, urgency, or anything like that. So in that case, you would need to be holding. And when you're holding, the most important question again is like, how much longer can you still hold, right? So for what amount of time can you still be holding? And this is what we're going to examine right now. And unfortunately, we're not going to go into very deep detail and to find an exact mathematical solution to the question of endurance, but rather what we're going to do is we're going to make a simplification which gives us enough, certainty still to examine the functions which are going to affect altogether the endurance. So the simplification is going to be that we're going to say that the endurance is inversely proportional. It's going to be inversely proportional to the fuel flow. So 1 over V. And I think that should make sense, right? Because let's think about it. Let's say that you have 1,000 kilograms of fuel on the aircraft, right? And you're consuming, so you have 1,000 kilograms of fuel on board. And let's say in the first example, your fuel flow is going to be 250 kilograms per hour. So from this, you can easily calculate that in that case, your endurance is going to be the, let's say, X fuel, right? So the X amount of fuel that you have on board over with the fuel consumption, right? So the 1,000 kilograms of fuel over with the 250 kilograms per hour. And in this case, we can see that the endurance is going to be 4 hours, right? In this case, you have 4 hours of endurance from the 1,000 kilograms of fuel if you're burning 250 kilograms an hour. Okay, so let's say, you also have 1,000 kilograms of fuel on board. However, this is, more inefficient aircraft, or simply is, has a larger mass, so therefore requires to have a larger fuel flow. So let's say for this aircraft, you have a fuel flow of 500 kilograms per hour. Now, in this case, let's continue it right here below. So endurance for the second case is going to be the X amount of fuel that you have on board over with the second fuel consumption. So you have 1,000 kilograms of fuel on board and you consume 500 kilograms an hour. Well, it's pretty easy to see that your endurance is simply going to reduce down to 2 hours, right? So your fuel flow doubled, so therefore your endurance dropped to half, right? So fuel flow doubled, so your endurance dropped to half. So it's definitely visible that they're inversely proportional to each other, and they're basically determined by how much fuel you have on board, okay, and the fuel flow of the aircraft. So in that case, we can examine 2 cases. So the first one is going to be the endurance of the jet. So the endurance for the jet is going to be inversely proportional to the fuel flow of the jet. However, the fuel flow of the jet, if you remember, we expressed as the specific fuel consumption for the jet, which is a thrust-specific fuel consumption times the thrust required, right? And we're going to be talking about steady-state cruising conditions, because when you're going to be in the hold, it's basically cruising conditions. So your altitude is not going to be changing most of the time. So we can say that this is going to be equal to the 1 over specific fuel consumption for the jet times the drag. Because again, this would be thrust required. You could understand this is thrust required. So altogether, we can see that this endurance is going to be very much a function from one side, from the specific fuel consumption, right? So how much fuel is this aircraft or engine rather consuming to generate a given amount of thrust? That's what this is telling us, right? And if this specific fuel consumption is large, that means that the aircraft is inefficient, right? So if this specific fuel consumption is increasing, then the entire fraction is going to decrease, and therefore your endurance is going to decrease, right? So that's, I think, pretty straightforward. And it's also going to say that if your thrust required or your drag increases, that also going to have the same effect. So in that case, your endurance, the time which you're able to spend airborne, is going to therefore reduce. So both of these effects is quite detrimental. However, there comes a question like, at what velocity do we need to maintain as pilots so that we get the best endurance? So to examine that, we will say that the endurance for the jet is going to be proportional to the inverse of the specific fuel consumption of the jet times the inverse of the drag. We're going to say that the specific fuel consumption, so therefore this entire fraction is going to be a constant. And we can definitely say that the endurance is going to be largest when the specific fuel consumption is lowest. So the more efficient engine you have, the higher endurance that you have from a given amount of fuel. But I think that makes perfect sense and doesn't need to be explained pretty much further. The second part is more interesting. So we're going to see, so we want to maximize endurance for sure, right? So we're looking for the max endurance. So therefore, we're going to be looking for the max of the 1 over drag. So therefore, we're going to be looking for the min of the drag component, right? So because where the drag function is minimum, the 1 over drag function is going to be a maximum. And I think you can already see where this whole process is going. However, let's just plot it just to make sure that there's an absolute clear understanding of the situation. So of course, we're going to be looking at the drag which is generated in function of the true airspeed for the jet. And we're just very simply looking for the value where the lowest drag occurs. All right, so the minimum of this drag function right here. And of course, you know, very straightforward, that is going to occur at the VMD by definition. So the minimum drag speed, and here's where the lowest drag occurs, right? So therefore, we can very plainly see that the best endurance for the jet is going to be at the VMD, and that's our final verdict here. So the best endurance is going to occur exactly in the VMD. Okay, so of course, all of the influencing factors which we could be looking at are going to influence the endurance in such a way that we would expect them. For example, what do you think the effect of the mass is, right? So when you increase the mass of the aircraft, what happens? So when you increase the mass of the aircraft, well, in that case, the entire curve, as we know by this point, is going to be shifted up and to the right. right, with regards to the true airspeed. So we have the initial drag right here, and you have the VMD for the light airplane, let's say, VMD for the light airplane, and the drag min, so the min drag for the light airplane, this drag curve for the light airplane, and when you increase the mass, the whole curve is going to be shifted up and to the right, so therefore your VMD for the heavy aircraft is going to increase, and of course the minimum drag for the heavy aircraft is going to be up here. Let me just try to draw it more precisely, so it's going to look like this. So this would be your drag for the heavy airplane. And so this is what's visible. If your mass is going to increase, in that case your endurance is of course going to decrease, right? Because we said that the endurance is going to be inversely proportional with the 1 over drag times the specific fuel consumption for the jet, right? And so if your drag increases in any way, your endurance is going to reduce. So this is the effect, and of course you would have the same situation for configuration. Of course, if you have configuration, the whole curve is going to be shifted up and to the left like this. So this would be your drag configured. So we would move up and to the left, and of course your VMD would occur at a lower speed, the configuration, and altogether your drag, your minimum drag would be higher. So if you use configuration, you have the same effect. Your endurance is going to reduce. So this is why you would hold with an aircraft, for example, in clean configuration. You wouldn't put your gear down, you wouldn't use flaps, which is actually a little bit counterintuitive. So you would think that with the lower speed you hold, the more endurance you have, right? But you can see that this is not the case. It is true that you're holding with the lower speed, so therefore it's true that the distance which you cover in a holding like this, for example, is going to be smaller. However, altogether, because your drag has increased, your endurance altogether is going to be reduced. So it's not always, the lowest speed which you can achieve that you're looking for when you're holding. This is why we don't use configuration when we're holding. We're flying in clean configuration and as close to the VMD, or on the Airbus as they would say, like the green dot speed as possible. Right, so that's your effect. And of course it's visible that the pressure altitude for the jet has no effect on the endurance. It's very interesting, right? Because what the pressure altitude does with the drag curve, it just simply moves it horizontally. Just to quickly sketch it for you right here. So we have the true airspeed, we have the drag, and let's say we have the drag for the sea level, so DH0, and then after that we would increase your pressure altitude, let's say to this one, DH1, and then further increase it, DH2, where H2 is a higher pressure altitude than H1, and H1 is higher than H0. And what we can see is that the minimum drag is going to be essentially the same, just at different velocities. So it's just going to occur at different velocities altogether. However, the value for the drag is a constant. So therefore we can see that for the endurance, the 1 over specific fuel consumption times the drag is going to be a constant, in function of the pressure altitude, and the specific fuel consumption is also a constant, as we already agreed. So therefore, the endurance is also going to be a constant in function of the pressure altitude, right? So this is how it's affected, basically. Okay, so the next area which we're going to be looking at is the effect of, or basically the endurance for the turboprop driven aircraft, so the propeller one. So we also said that the endurance is inversely proportional to the fuel flow, so this is where we will begin the discussion from. So endurance for the prop is inversely proportional to the fuel flow of the prop. Right, so the fuel flow for the prop, if you remember, is going to be the 1 over specific fuel. So the fuel flow itself is one of the specific fuel consumption for the propeller-driven aircraft and times the power. And since we're going to be talking about a cruise condition, we're going to say that this is going to be 1 over the specific fuel consumption for the propeller times the power required, right? And so this is what we're going to look at, and we can see that definitely the influencing factors for the propeller-driven aircraft for the endurance are going to be the specific fuel consumption, the power-specific fuel consumption of the aircraft, which means, you know, the amount of fuel required to generate a unit amount of power. So it's an engine consideration, basically, and of course the power required, or is going to be dependent on the amount of power required. Okay, so we want to look what factors influence the endurance, and we want to also see at which speed are we going to have the best endurance for the propeller-driven aircraft, right? So to understand that, we're going to break the endurance into two components. So we have the endurance for the prop. We're going to say it's going to be inversely proportional or proportional to the inverse of the specific fuel consumption for the prop times the 1 over power required. Okay, so we already said that we're going to presume the specific fuel consumption for the propeller-driven aircraft as well to be a constant. However, this is going to be more interesting for us. So we're looking to maximize the 1 over the power required. So therefore, we will try to minimize the power required. And I think, again, it's very evident from the previous case where this discussion is going to be going. However, still, let's plot it and make it even more clear. Okay, so we're going to have a coordinate system with the power and the true airspeed. So let's plot for ourselves the power required, which has a very similar shape again to that of the drag. It's just steeper. So at exactly where will this minimum power required occur? Of course, by definition, is going to occur at the VMP, which is again by definition the minimum power speed, and of course here you have the minimum power required, right? So in a general case, we can say again that for the propeller-driven aircraft, the best endurance occurs at VMP. And this is what we have to remember from this whole thing. And from that, we can examine the influencing factors. So we will see that, for example, increasing the mass is going to shift the entire power required curve up and to the right? So it's going to be somewhere right here. So this would be your power required heavy. And here would have the VMP for the heavy aircraft. And if you configure it, it's going to move up and to the left. So we're here. So this would be your power required for the configured aircraft. And this would be your VMP for config. Right, so altogether we can see in both cases that the power required, so the min power required, and altogether the power required has increased in both cases, contrary to the clean and the light aircraft. So therefore, we can say that if you increase the mass, your endurance for the prop is going to decrease, and if you configure the aircraft, your endurance is going to decrease as well. Right. What happens with the pressure altitude? Now that is a bit more interesting question. Like, what happens in function of the pressure altitude, or how does pressure altitude influence the endurance of the propeller-driven aircraft? We already saw in the case of the jet that for the jet, the pressure altitude had no influence, because despite you need to maintain a higher true airspeed to have the same amount of drag, despite that, we saw that the amount of drag, the amount of the actual drag generated had no change, right? So it was a constant. So we said that for the jet, the pressure altitude does not influence the endurance. However, it's going to be a bit different for the propeller-driven aircraft, and we're going to see exactly why. So we're going to plot again the power in function of the true airspeed. So let's say that here we have the power required for the sea level, HO. So what happens to the power required curve if you increase your pressure altitude? I'm going to leave you guys a little bit of time to think about it. Well, the right answer is that it moves up along the tangent, right? So somehow like this. This would be your power required at a higher pressure altitude, and this would be your power required at an even higher pressure altitude, right? So it moves like this, up along the tangent, right? And we would say that the H2 is higher than the H1 and is higher than the H0, and these are all pressure altitudes. All right. So what we can see for these cases is that for one thing is that the speed where the minimum power occurs for the different pressure altitudes is going to increase in function of the pressure altitude increasing. This is one thing. And the second thing is that the minimum amount of the power is continuously increasing, right? And this is true at any speed. So even if the minimum power required is increasing, therefore for any other speed you would see an increase in the power required as well. So what we can see definitely happening is that the power required is increasing. And if the power required is increasing, what happens to the endurance? Well, if in the denominator this part is increasing and this one is a constant, in that case we can see that the entire fraction is going to decrease. So therefore, because it's proportional, the entire endurance is going to decrease with a higher pressure altitude. Right? So we can say that for the propeller-driven aircraft, if your pressure altitude increases, your endurance decreases. And this is what we have to sort of remember here, that for a propeller-driven aircraft, actually it is more beneficial to hold at a lower altitude as close to the sea level as possible, whereas with a jet it doesn't really matter, right? So this is what we can see from this diagram and from this idea altogether. All right. So we already discussed the effect of mass on the endurance. So of course we said that a lighter aircraft is going to have more endurance, whereas a heavier aircraft is going to have less endurance. And we're going to say right here that for the turbojet aircraft, so for the turbojet aircraft, when holding or flying with VMD, the endurance, so this is where the induced drag is equal to the parasite drag, and at this speed only, the fuel flow is going to be proportionate to the mass of the airplane. So what this means is that if you have two masses for the aircraft, so mass 1 and mass 2, you're also going to have fuel flow 1 and fuel flow 2, where the fuel flow 1 basically belongs to the mass 1, right? Or is the function of the first mass, and the fuel flow is going to be the function of the second mass, right? So therefore what we can say is that the B1, so the fuel flow in the first case over the fuel flow in the second case, is going to be the mass of the aircraft in the first case over the mass of the aircraft in the second case. And this is going to be the formula that we're going to be using to solve the calculation problems which are given to us during the CAA exams. And this is only true for VMD and for the jet, right? To give you an example, to my understanding, the same example is used in the Pet Pilot book. So in the example, we're going to have an aircraft mass of 56,000 kilograms, and is going to have a fuel flow of 2,400 kilograms per hour. And the question is, what is the fuel flow at 48,000 kilograms? Okay, so therefore we can collect the information that was received. So the aircraft mass initially is 56,000 kilograms. And the fuel flow initially, which belongs to the initial mass, is going to be 2,400 kilograms per hour. So what is the fuel flow at the second case, when the mass of the aircraft is going to be 48,000 kilograms? Okay, so let's use the formula. So B1, so the fuel flow 1 over the fuel flow 2 is going to be equal the mass 1 over the mass 2, right? So what we're looking for, the unknown, is going to be the B2, the fuel flow in the second case, so we can further express this equation to the following way. So we're going to express the fuel flow in the second case, which is going to be equal to the fuel flow 1 times the mass 2 over the mass 1, right? It makes sense. We multiply with B2, then we multiply with M2 and divide by M1 to get to this expression, right? So we have everything we know on the right, or sorry, everything we don't know. No, it was correct. So everything we know on the right? Because we know the B1, the M1, and the M2, and we have all of the unknowns on the left side right here. Right, so we can, from this, we can go ahead and calculate. The mass flow, so is going to be the B1, which is 2,400 kilograms per hour, multiplied by 48,000 kilograms over 56,000 kilograms. And you can put in here actually the dimensions, right? So this is going to be kilogram over kilogram, and this is kilogram per hour. So this whole thing checks out, right? Because you can simplify with the kilograms, and you're going to have kilograms per hour, a final dimension to this whole thing. And this is exactly the dimension for the fuel flow, so that checks out. And also you can visibly see that you're going to be multiplying the initial fuel flow with the ratio, which is the ratio of the change of the masses, right? So what you're going to get as a final answer to this calculation is that your fuel flow is going to be equal to 2057 kilograms per hour. Right. And here, let's take a step back and check what we have. So we said initially that we would presume that a heavier aircraft has a smaller endurance, or and therefore you know, a smaller fuel flow, right, altogether, and or sorry, a larger fuel flow. And here what we have is that in the second case our mass is less, so therefore our endurance is going to be larger, so therefore the fuel flow is going to reduce. And this is exactly what we have, right? Because our initial fuel flow was 2,400 kilograms per hour, and now our fuel flow is 2,057 kilograms per hour, and that checks out, right? For a lighter airplane, we need, you know, a lesser fuel flow, actually. And I think it makes sense because we multiply the initial fuel flow with the ratio of the masses, and in this case you can see that we're going to receive a number which is less than 1. So therefore your fuel flow is definitely going to be smaller than the initial one, so the calculation checks out. And you can expect calculations like this, where they would be asking either for the mass of the second aircraft based on the secondary fuel flow, or so you're going to either have to calculate mass or the fuel flow or the mass of the aircraft in one or the other stage, right? So I think it makes sense. It's not too difficult of a calculation, and you just always need to use this sort of formula, because you're not going to given a case when the aircraft is not flying at VMD or is not a jet. So anytime you're given this kind of formula or this kind of exercise, you're just going to be using this formula like we did in this example. So altogether, this was it for the endurance. We're finished with this part, and in the next video we're going to be continuing with talking about the glide and the descent. Okay, so thank you for your attention in this video, and I'll be seeing you guys in the next one.